Welcome to all of you. This is the 8th session of our discussion on quantum mechanics part 2, which belongs to BSc Physics course, 6th semester, paper 8. This is Narayan Sharma. Here I am continuing my discussion on linear harmonic oscillator. In my previous session, so we discussed about linear harmonic oscillator. We wanted to obtain an expression for energy eigenvalues, and of course we want to write expression for the energy eigenfunctions also, and we are continuing our discussion. Again, just briefly, I would like to mention the objectives. This I have already been mentioned. So the objectives of my previous session and this session is to apply Schrödinger's equation to a linear harmonic oscillator. And we want to derive an expression for the energy eigenvalues. We want to calculate the wave function of the oscillator also. And of course, we want to plot the wave functions that is associated with one-dimensional linear harmonic oscillators. So let us continue the discussion. So we were trying a solution of the form psi is equal to f of y exponential minus y squared by 2 in the previous equation. Please refer to my previous video so to see the equation 9. So therefore, we are trying to obtain the solution of the differential equation associated with the linear harmonic oscillator one-dimensional case in terms of y. So the solution can be written in the form of f of y into exponential y square minus by 2. Once we substitute this solution into the previous equation, equation number 9, then we get a differential equation in terms of f. So the differential equation that we are going to get is d square f by dy square minus 2y df by dy plus alpha minus 1 times f is equal to 0. So we have got another differential equation term in terms of f. And once we are able to find out the solution of this equation, then we can substitute back in this equation. And therefore, it is possible to find out the complete wave solutions, complete wave function of the linear harmonic oscillator. So there is a standard procedure of solving this differential equation, and that the standard procedure is nothing but, so assuming that f of y can be written in terms of the power series. So this f of y can be written as a0, so plus a1 times y1 plus a2 times y square plus a3 times y cube plus etc etc etc, or in the summation index we can write it as summation n running from 0 to infinity of en to the power of yn. So this is essentially a power series. So we have assumed that f of y can be expanded in terms of the power series, and therefore the power series solution is actually given by equation 11. And if we differentiate this equation 11 with respect to y, what we are doing is we are assuming the solution and we are differentiating. So, and we are obtaining the different terms, and we substitute those terms in equation 10, and we are trying to obtain the necessary solution or the necessary conditions, whatever we get. So therefore, if I differentiate equation 11, so then I'm going to get, so df by dy is equal to differentiation of a0 is 0. So differentiation of a1 into y1, a1 is constant, so differentiation of y1 is 1. So therefore, we have a term of 1. Then differentiation of a2 y2 square is a2 2y, or it is 2a2y. Similarly, differentiation of a3 y cube is 3a3y square, etc etc etc. And this whole term can be written in terms of summation index. So where n runs from 1 to infinity of n y to the power of n minus 1. This is very trivial. So we have a term of y into df by dy in equation 10. So therefore, we want to multiply this equation 12 with y. So once we multiply this above equation 12 with y, so we are going to get a2 into y. So 2a2 into y square, 3a3 into y cube, etc etc etc. And therefore, once we are able to write power series expansion, so we got an equation. So it says that summation n running from 0 to infinity n y to the power of n, that is equation 13. Also, we have a term of d square f divided by dy square. So therefore, in order to obtain this equation, we want to differentiate once again. So once we differentiate equation 13 once again with respect to y, then we are going to get d square f divided by dy square. It is very simple. So as per equation 12, so differentiation of a1 becomes 0. Where we have second term 2a2y, differentiation of 2a2y becomes a 2a2. So therefore we have written as 1 into 2 into a2. And differentiation of the third term is 3a3y square. It is 2 into 3 into a3 into y. And the third term can be written as 3 into 4 into a4 into y square. And the whole thing can be written in the summation index as, so summation n running from 2 to infinity, n into n minus 1, an y to the power of n minus 2. In order to make this series starts from n is equal to 0, we need to do a small change. And once we do the small change, we are going to get summation. So n is equal to 0 to infinity, n plus 2 into n plus 1, an minus 2, y to the power of n, that is equation 14. So therefore, so we have got so two different terms, d square f divided by dy square as per equation 14, and also we have got the term y into df by dy. So this is equation 13 and equation 14. We are substituting equation 13 and equation 14 back into equation 10. Once we do that, so then we are going to get, so summation is common for all the terms. So therefore we can write it as summation n running from 0 to infinity of n plus 2 into n plus 1 a of n minus 2 minus of 2n plus 1 minus alpha an. So outside the bracket we have a term of y square that is equal to 0. So therefore, in order to this equation to hold all values of y, so if we want this equation to hold good for all the values of y, so then the quantity in the brackets must be 0 for all values of n. Irrespective of the value of n, so we can say that, so the term that is existing within this square brackets must be 0. So therefore, once we equate the terms, so within the square brackets to be equal to 0, we get a condition, and that condition becomes equal to n plus 2 into n plus 1 into an minus an plus 2 is equal to 2n plus 1 minus alpha into a. And if we simplify this equation, we are going to get an plus 2 is equal to 2n plus 1 so minus alpha divided by n plus 2 into n plus 1 into an. So this is equation 16. This equation 16 is what we call it as a recursion formula. When calling it as recursion formula, it is because if I substitute n is equal to 0 here, then I'm going to get a0. And if I substitute a0 here, then I'm going to get 0 plus 2 a2. That means if I know the value of a0, then it is possible to calculate the value of a2. Similarly, if I substitute n is equal to 1 here, then in the left side I'm going to get a of 1 plus 2, that is a3. That means if I know a0, it is possible to generate a2, a4, a6, etc., etc., etc. And if I know the value of a1, then it is possible to find out the values of a3, a5, a7, etc., etc. So in this sense, this equation is what we call it as a recursion formula. So it is because either by knowing the value of a0, by knowing the value of a0 and a1, it is possible to generate all other possible values of a. For example, a2, a3, a4, a5, etc., etc., etc. So that's why this particular formula is what we call it as recursion formula. There is a little more mathematics that I am avoiding here. So directly I'm substituting here. It can be proved that the wave function psi would vanish to 0 as y tends to infinity. Please remember, so for any system, so we want to call the wave function of the system as a proper wave function, then that wave function must vanish 0 as, so the respective independent parameter x or y, whatever it is. Here in this case it is y, and y tends to infinity. We expect our wave function to vanish at infinite large distances. Okay, so this is what the thing. So therefore, we can say that, so when f is a polynomial of finite number of terms, so wave function psi of a linear harmonic oscillator would be a wave function which would vanish to 0 as y tends to infinity, and that is possible only when, so the polynomial f of I that we are discussing should be a polynomial of finite number of terms. It should not contain infinite number of terms. If it contains infinite number of terms, then the wave function would not vanish to 0 as y tends to infinity. So in order to make psi vanished to 0 as y tends to infinity, we expect f to be a polynomial of finite number of terms. And this is possible. So f would be a polynomial of a finite number of terms. If it is, this is possible only when the numerator in the equation section becomes 0. So this is a little bit involved. We're not discussing all these things mathematics here. But anyhow, directly I'm mentioning the condition. Such a thing is possible only when the term in the numerator of this equation section, that is 2n plus 1 minus alpha, must be equal to 0. Let us see what is going to happen when this term 2n plus 1 minus alpha becomes equal to 0. So therefore, we are going to get a condition which says that alpha is equal to 2n plus 1. But we already know the value of alpha. The value of alpha can be written as 2e by h nu naught, where E is energy of the oscillator, h is Planck's constant, nu naught is what we call it as classical frequency of oscillation of the oscillator. So therefore, if I substitute the value of alpha here, and if I do the simplification, then I'm going to get energy E as something like E is equal to n plus 1 by 2 h nu naught. Since energy E is a function of n, a quantum number, this quantum number n here in this case is what we call it as vibrational quantum number of the oscillator. So therefore, we are writing the expression for energy as En. En is equal to n plus 1 by 2 h nu naught, where n, the possible values of n are 0, 1, 2, 3, etc., etc., etc. So please, we have to keep it in mind that the possible values of this quantum number n, vibrational quantum number, are 0, 1, 2, 3, etc., etc. Unlike the case where we discussed a particle in a one-dimensional box, there also we encountered with one quantum number, and the possible values of the quantum number in the case of a particle trapped in a box is something like 1, 2, 3, excluding 0. But here in the case of your linear harmonic oscillator one-dimensional case, n is equal to 0 is also allowed. This is of some special significance we are going to discuss about. So therefore, anyhow, equation 17 says that En, which is equal to n plus half into h nu naught, gives the energy eigenvalues of the linear harmonic oscillator. Equation 17 represents energy eigenvalues of linear harmonic oscillator. So if I substitute n is equal to 0, then I'm going to get a value of E0 is equal to half h nu naught. And that is what? Nothing but the energy of the oscillator in the ground state. N is equal to 0 corresponds to ground state of the oscillator. Similarly, if I substitute n is equal to 1, that actually corresponds to energy of the oscillator in the first excited state. If I substitute n is equal to 2, then we are going to get the energy of the oscillator in the second excited state, and so on. Let us come back. So if I keep on substituting the values of n as 0, 1, 2, 3, then we are going to get half h nu naught, 3 by 2 h nu naught, 5 by 2 h nu naught, etc., etc., etc. So clearly we can say that the energy levels of the harmonic oscillators are quantized in steps of h nu naught. Otherwise, the energy difference between any two successive levels in the case of a harmonic oscillator is the same, is equal. The energy levels are equally spaced with energy difference of h nu naught, where nu naught is the classical frequency of oscillation. So the energy levels are here evenly spaced. So we are going to discuss a case which is called rigid rotator, where the energy levels of the rigid rotator are not equally spaced, which we will discuss in later. Anyhow, here we can say that the energy levels of the linear harmonic oscillators are evenly spaced because the separation is a constant value. And that constant value of separation is h nu naught. That is very clear from this particular expression 17. Now, if we substitute n is equal to 0 here, I have already told n is equal to 0 corresponds to the ground state of the harmonic oscillator. So therefore, if I substitute n is equal to 0 here, then we are going to get the energy of the oscillator as E naught is equal to half h nu naught. Clearly, as nu naught is not equal to 0, E naught, energy of the oscillator in the ground state, is also not 0. So therefore, which is the lowest value of the energy of the oscillator can have. So this is what we call it as a 0 point energy. So 0 point energy is of great importance. It is because, as per classical theory, classical physics, so if an oscillator is in the ground state, it should not be oscillating, and therefore its total energy in the ground state must be 0. But according to quantum mechanics, we are getting completely a different result, as per which, so when the oscillator is in the lowest state, the ground state, then also, so the total energy of the oscillator is not 0, and it has a finite value of half h nu naught. So this value of the energy of the oscillator, so in the ground state, so of an oscillator, is what we call it as 0 point energy. So 0 point energy, because an oscillator in equilibrium in surroundings with the approach energy of E is equal to E naught half h nu naught, as E naught is equal to 0 as the temperature approaches 0. According to classical theory, so as the temperature approaches 0 Kelvin, then definitely the energy of the oscillator must be 0. But according to quantum theory, quantum mechanics, so our discussion of Schrodinger application of the Schrodinger equation to linear harmonic oscillator, clearly we can say that as the temperature of the linear harmonic oscillator approaches 0 Kelvin, then also the energy of the oscillator would not become 0. It would attain a finite value of half h nu naught, when nu naught is the classical frequency of oscillation. So therefore, this particular energy is what we call it as 0 point energy. And 0 point energy is also closely related with Heisenberg's uncertainty principle. Just I would like to mention that even using Heisenberg's uncertainty principle, it is possible to calculate 0 point energy of the oscillator to be equal to half h nu naught. That means even using Heisenberg's uncertainty principle, it is possible to show that 0 point energy of the oscillator is not 0. It is actually given by half h nu naught using Heisenberg's uncertainty principle. Clearly, otherwise, we can also say that so the 0 point energy comes all because of the Heisenberg's uncertainty principle. Our linear harmonic oscillator is a system which so strictly obeys so Heisenberg's uncertainty principle, because of which the energy of the oscillator in the ground state would not come out as 0. Instead, it would come out as half h nu naught. This is of a great significance as per the quantum mechanical point of view. Let us continue the discussion. And the polynomial f of y that is mentioning, so the power series that we were expecting is nothing but hn, is written as hn of y. H of y, a function of y. It also depends on the quantum number n, vibrational quantum number n. So therefore, the polynomial f of y is nothing but hn of y, and this hn of y is what we call it as Hermite polynomials. Hermite polynomial of the order n. For example, if I substitute 1 here, so then I'm going to get Hermite polynomial of first order. If I substitute n is equal to 2, so then I'm going to get Hermite polynomial of second order. Extremely sorry. If I substitute n is equal to 0, then I'm going to get Hermite polynomial of first order. If I substitute n is equal to 1, then we are going to get Hermite polynomial of second order, and so on. It all depends on the value of n. When value of n actually starts from 0 also. So therefore, it is possible to prove that the generalized normalized wave function of the oscillator of the order n is given by. So this is what the derivation we have not done. It is not necessary to this. Okay, this involves a little bit of mathematics. So therefore, we are avoiding the mathematics here. So without doing much of the mathematics, it is possible to prove that the normalized wave functions of the oscillator, so of the order n is the vibrational quantum number, is actually given by psi n is equal to 2m mu naught by h cross whole to the power of 1 by 2, 2 to the power of n factorial whole to the power of minus 1 by 2, hn of y into exponential minus y square by 2. I have already told hn of y, they are nothing but Hermite polynomials. Here I have mentioned some of the Hermite polynomials. So for our reference sake, we substitute n is equal to 0. That means h0 of y. h0 of y is nothing but a Hermite polynomial, which is nothing but a constant, and that constant comes out to be equal to 1. If I substitute n is equal to 1 in the expression of the Hermite polynomial, that is h1 of y, h1 of y is nothing but equal to 2y. And if I substitute n is equal to 2, h2 of y, then h2 of y actually corresponds to a function of 4y square minus 2. Similarly, if I substitute n is equal to 3, then we are going to get h3, so 8y square minus 12y. Similarly, if I substitute n is equal to 4, then we are going to get Hermite polynomial corresponding to n is equal to 4, which comes out to be equal to 6y square minus 14y square plus 12. So these are some of the Harmonic polynomials. And once we want to calculate so the wave function for the different states, for example, if I want to calculate the wave function in the ground state, then I have to substitute n is equal to 0 here. If I substitute n is equal to 0 here, then I'm going to get 2n mu naught by h plus 1 to the power by 2, and this whole term would vanish, actually become 1, and this h n of y would become equal to 1, then I'm going to get e power minus y square by 2. Similarly, it is possible to calculate the wave function of the normalized wave function of the oscillator for different states, either for the ground state or for the different excited states. So we can make use, we can calculate the wave function using this table for first few states of the oscillator. So therefore, we can say that equation 18 actually represents Harmonic polynomials, or equation 18 actually represents the normalized wave function of the oscillator for different states of the linear harmonic oscillator. Let us proceed. We want to discuss, I told we want to plot the graph of the wave function of the oscillator for different orders. Here I have shown the variation of the wave function as a function of distance along x-axis corresponding to n is equal to 1, n is equal to 0, n is equal to 1, n is equal to 3, and n is equal to 4. So if we substitute n is equal to 0, then classically we have two extreme regions. So one of the extreme region is x is equal to minus a, another extreme region is x is equal to plus a. Classically, our oscillator can undergo oscillation between two extreme positions. So this is one of the extreme position, x is equal to plus a is one of the extreme position, x is equal to minus a is another extreme position, the negative x direction. So, but according to this particular variation of the wave function, what we have written here, so our wave function of the oscillator can exist even beyond those two limits, x is equal to minus a and x is equal to plus a also. That means a quantum mechanical oscillator which is oscillating between two extremes can have a probability of finding even beyond those extremes also. For example, beyond x is equal to plus a, we can see that the wave function has a certain height here. That means there is finite but small probability of finding the particle even beyond the region x is equal to plus a. The same thing is applicable to the region x is equal to, beyond the region x is equal to minus a region also. Classically, we expect our oscillator to oscillate only between the limits x is equal to minus and x is equal to plus a. But the thing is, according to quantum mechanics, there is a finite probability of finding the particle, which is executing linear harmonic oscillations even beyond the regions x is equal to minus a and x is equal to plus a. Similarly, we can show the same thing for different regions, different wave functions. Even in the case of n is equal to 1, the variation of the wave function goes in this manner. So the probability of finding the particle exactly at the midway becomes 0. In the ground state, probability of finding the particle and the probability of finding the oscillator exactly at the equilibrium position is maximum. Whereas if I go to the first excited state, in the first excited state, probability of finding the particle at the equilibrium position is 0, because the value of the wave function vanishes in the midway, the equilibrium position. Once the value of the wave function becomes 0, then the modulus of the square of the modulus also becomes 0. So therefore, we can say that the probability of finding the particle at the equilibrium position is 0 when the oscillator is in the first excited state. Similarly, we can explain the variations for different excitation states of the oscillator. So this is what a small discussion about linear harmonic oscillators. So I'm stopping my discussion here. So we shall continue our discussion in the next session with one more topic. I thank you all.